I'm back. We looked at class 1 in the last video. Class 1 lever. We remember that our class 1 lever, the thing that was in the middle was our fulcrum. Okay, so the classes of lever are always designated by the thing that happens in the middle. So we've got a fulcrum, and we're applying an effort force, and we have a load force. Okay, so middle is our class of lever. So we know class 1 is this, okay, fulcrum in the middle. But we're dealing today, or for this video, with our velocity ratio calculation for a class 2 lever. So if we don't have the fulcrum in the middle, we've got two choices. We've either got the load in the middle or the effort in the middle. And for this type of lever, the classic example of a class 2 lever is a wheelbarrow. And if you think about a wheelbarrow, you're lifting the weight, it pivots at the wheel at the front, so the load is in the middle. So for class 2, load is in the middle. Okay, so class 2 lever, sometimes see it written with the Roman numerals. Load in the middle. Okay, so we know class 1 fulcrum in the middle, load in the middle. Now, the velocity ratio equation, which is written in full here, velocity ratio equals distance of effort over distance of load, is the same for all the classes of lever, class 1, class 2, and class 3. And this is a simple way of writing it. D subscript E, distance of effort, D subscript L, distance of load, okay? The only difference is you need to know how to work out what distance of load is and distance of effort is for class 2. And the first time I did it, I got it wrong. Okay, so we're going to think about our wheelbarrow. It pivots on the wheel. Okay, so we're going to think about the wheel as being a fulcrum. So it's going to be at the front of our lever. Then our lever is here. Okay, and our load is here. Okay, now we're going to assume for the example of this problem, later on we do moments and we talk about perpendicular distances and it gets a little bit more confusing. We're going to assume that we're dealing with a horizontal situation. Okay, so that's our wheel of our wheelbarrow. That's our load. Might be a big mound of sand or 100 tons of bricks. And we're applying our force of effort this end. And we've got our force of load, F of load, happening down this way. And we have our fulcrum here. So we need you to work out how we're going to work out our distance, okay, effort, distance of load. Now the first time I did this, because I was thinking about the middle with our class 1, I thought, well, that'll be force of effort from here to here, and this will be force of load from here to here, okay? Wrong. Because you're always measuring reference to the fulcrum. Okay, so our force of effort is not from here to here, it's from here. Sorry, our distance of effort is from here to here. Okay, so distance of effort is measured from where the effort's applied to the fulcrum. First time I did it, I measured from here, to the center, because this is what I did with class 1. But we're going reference to the fulcrum, okay? So that's the first thing you need to know, that if I want my distance of effort, it's going to be from there right to the fulcrum, okay? This is distance of effort, D subscript E, okay? From where the force of effort is applied to the fulcrum. Now, distance of load is from the fulcrum to the load, okay? So that's kind of the same, okay? So that's distance load. So we can use our velocity ratio equation over here, dE over dL. So say we've got a distance of effort, like in our last equation of 100 meters, and our distance of load is going to be equal to 10. We can work out a velocity ratio. We can say VR is equal to distance of effort, dE over dL, which equals 100 meters, distance of effort, okay? The distance of effort from there to there, 100 meters, over our distance of load from there to there, 10 meters, okay? 100 divided by 10 equals 10. So what that basically means is, if I've got 100 kilos of bricks in my wheelbarrow, it's 100 times 10, the force of gravity. We'll talk about that later, but you should know that formula anyway. you've got 1,000 newtons pushing down, right? You don't need to apply 1,000 newtons of force to lift that, okay? You only need to apply 100 newtons to lift 1,000 newtons, okay? So it's magnifying your 100 newtons by 10, okay? Because we have a VR of 10, okay? So main thing to take away from this lesson, in summary, is that a class 2 lever has the load force in the middle, and the only difference is when you're measuring your distance, remember that your distance of effort doesn't go to the load, it goes all the way to the fulcrum, okay? And distance of load is from the load to the fulcrum, so we reference to the fulcrum, okay? If you do that, you'll get these questions correct. Okay, and like I said, for our class 1 is a seesaw. Now, the only difference with this one too is class 1, you push down one end, it goes up, push down the other end, it goes this way because the fulcrum's in the middle. For this class of lever, whatever direction you move your effort, the load moves in the same direction. So there is a change in that respect too. And the other thing with a class 1 is you can have a velocity ratio in class 1 that's less than 1. Okay, so if I make my distance effort really short and my distance load really long, that's going to be, this is distance effort, and this is distance, this is force of effort here, and this is force of load here. You can see that the distance of effort is much shorter than the distance of load. That's a disadvantage. Okay, so you can make your VR less than 1, you can make it way greater than 1. I mean, Archimedes said, give me a lever and give me a fulcrum and a lever that's long enough I can move the entire world. This is kind of true, but it's a very strong lever. With class 1, you can have velocity ratios below 1, greater than 1, okay? But for our class 2 lever, our velocity ratio is always going to be 1 or greater, because you can only move your load as far as a distance. So you can have a distance load from here to here that's equal to your distance effort. 1 over 1 equals 1, or 100 over 100 equals 1. So you can have it 1 or greater, so you can have it balanced, or you can have it with a huge advantage to yourself, but you can't make it harder for yourself. Okay, so class 2 lever, if they ever say, can I have a class 2 lever with a velocity ratio that is less than 1? No, you can't. Okay, can on a class 1, not on a class 2. So class 2 is always 1 or greater for velocity ratio. Okay, keep that in mind, because sometimes they'll ask you that as a multiple choice question. And if you're not sure about it, play around with these distances and work it out for yourself. But this equation for this type of lever, you can never make it less than 1, okay? Because your distance of effort can never be greater than your distance of load. Simple as that. Anyway, I hope that explains your class 2. We're going to do, like I said, I'm going to give you a page of examples, and we're going to do a few examples calculating velocity ratios for the various types of levers to make sure we understand this principle. See you next video.